The next lesson in our bonding and intermolecular forces unit is on molecular polarity. So the first three learning targets we have worked on identifying bond characters, drawing Lewis structures or dot diagrams, and looking at the shapes of molecules. These next two learning targets, 4 and 5, really start putting all these things together, where we look at how the shapes and the electronegativities can affect the overall properties of the molecule. In order to understand this, we really have to have a good understanding of each of these first three in order to get to number 4 here. So in this short video, we will look at defining polarity and determining the relative polarities of molecules. So molecular polarity. We know what a polar bond is. That's something we've been studying for a while now, and we know a polar bond is a bond where electrons are shared unequally, where one atom has a greater pull on the electrons than the other. But what makes for a polar molecule? How would I describe that? What situation would I describe a molecule as being polar? Well, a polar molecule is very similar to a polar bond. It's a molecule where we have more electron density on one side compared to the other of the molecule. In other words, there's an uneven distribution of electrons leading to partial charges on either side of the molecule, where one end of the molecule is partially positive, the other end is partially negative. Just like if we have a polar bond, we have one end of the bond is partially positive, the other end is partially negative, but now we're just applying it to the entire molecule. So an example of this, water is a great example. We're very familiar with water, it's very important to us. We know that a hydrogen-oxygen bond, not talking about the entire molecule, but just a bond between hydrogen and oxygen is polar, because oxygen is more electronegative than hydrogen. So if we have a bond between oxygen and hydrogen, the oxygen has an electronegativity of 3.5, hydrogen is only 2.1, so that electron density gets pulled towards the oxygen. Recall, as we've discussed in class, these electrons that are being shared, they're not stuck in place between the atoms. They're free to move from one atom to the other, but because of the greater electronegativity of oxygen, those electrons spend more time closer to the oxygen than they do the hydrogen, making that bond polar. Now, a water molecule as an entire whole is polar as well. This is because one side of the molecule has more electron density than the other. So if we were to look at a diagram of a water molecule, so now we're showing all the atoms where we have our central oxygen and the two hydrogens, and note it looks like this bent structure because that is the actual geometry of water. Just because we might draw a Lewis structure where the hydrogens are on either side of the oxygen making it look linear, we have to understand the geometry, and that's very important to us. Because when we think about the bonds here, each of these bonds is polar just as we showed above. The oxygen is pulling these electrons more strongly than the hydrogen. Well, this geometry of the molecule leads to a polar molecule because overall that electron density is getting pulled upwards towards the oxygen. We call this the overall dipole of the molecule. Where dipole, note the prefix in that word dipole, di meaning two. There are two poles or two ends to the molecule where the electrons are getting pulled unevenly. So the top end, as we have it drawn here, has more electron density than the bottom end, leading to the oxygen being partially negative and the hydrogens being partially positive. So as we'll see in this video and in all the examples we do in class, in order to understand the polarity of molecules, we must have an understanding of molecular geometries. Because as we'll see on the next slide here, where these hydrogens are in this molecule, the fact that these are bent, that this water molecule has a bent structure, makes a huge difference in the polarity of the molecule. So speaking of that, let's ask the question. If we have polar bonds in a molecule, does that mean the molecule itself is polar? Well, here is a great example to show us that this is actually not the case. Consider a carbon dioxide, CO2 molecule. So a bond between carbon and oxygen is polar, just like we said between carbon and hydrogen is polar, because oxygen is much more electronegative than carbon. In fact, the difference is 1. Oxygen's electronegativity is 3.5. Carbon's is only 2.5, so that electron density gets pulled towards the oxygen. But a molecule of carbon dioxide itself is actually not polar, and we'll see why. It's because of the geometry of the molecule. So here is a Lewis structure of carbon dioxide. I have my central carbon, and as it turns out, I'll need two double bonds, one going to each oxygen. Now the oxygen, as we said above, is more electronegative than the carbon. So that oxygen is going to pull on that electron density away from the carbon. But notice this molecule is linear. There are two electron groups around the carbon, and as we have learned, that means we're going to have this linear geometry. So this electron density is getting pulled equally in opposite directions. So the overall dipole here, if you think about adding up these two arrows, if you will, or these would be the individual dipoles of the two bonds, if I add those up, they're going to cancel each other out. So the overall dipole is none. Even though the bonds in the molecule itself are polar, the entire molecule is nonpolar because there's not one side of the molecule that has more electron density than the other. Here's another way of looking at it. Yes, each of the oxygens will be partially negative because they are going to have more electron density than the carbon. But the entire molecule as a whole, there is not one side of it that's partially positive and the other side is partially negative because this electron density is pulled equally in both directions. So what we're seeing here is that symmetry. If my molecule has perfect symmetry, where if I cut it in half, regardless on which plane or which axis I cut it in half on, if I cut it in half and it is the same on both sides, that's going to lead to a nonpolar molecule, because even if I have polar bonds, the electrons are going to get pulled equally in all directions, which will make it nonpolar. Alright, we also want to be able to determine which molecule is more polar than another, even if I have two polar molecules. So for example here, let's take a look at water and hydrogen sulfide. Which molecule between these two is more polar? And I picked these two because their Lewis structures are exactly the same. In fact, there's a name for this. We call this situation isoelectronic. That's not a term you guys need to remember, but you will see it from time to time if you study more chemistry, where these are the exact same Lewis structures, where my central atom, in this case sulfur and oxygen, they both have four groups of electrons, two bonds, two lone pairs. It's the exact same. Now, to answer which one is more polar, we have to first consider, are these two molecules polar? And the answer is actually yes, they are. They are both polar. However, one is more polar than the other. Let's figure out which one. So neither molecule has symmetry because of these lone pairs. Oftentimes, whenever a molecule has lone pairs, typically it won't have symmetry. You might be saying, but wait, if I cut it in half right down the middle here from top to bottom, it would be the same on both sides. And you would be right, on that axis it has symmetry. But what about if I cut it in half going right to left? The top is not the exact same as the bottom. And do remember as well, we have to think in three dimensions here. We have to think about the geometry of the molecule. So both of these molecules, the electron pair geometry would be tetrahedral, because there are four groups of electrons. Both of them would have a molecular geometry of bent, and that's why we draw the Lewis structures like this to show that they are bent. But consider this, the electronegativity difference between hydrogen and sulfur is only 0.4. Whereas the difference in electronegativity between hydrogen and oxygen is 1.4. So both of these, there's going to be a little more pull going towards the central atom because the sulfur is more electronegative than the hydrogen. The oxygen is even more electronegative than the hydrogen compared to the sulfur. So the overall dipole on the hydrogen sulfide is going to be pointed up towards sulfur, but it's going to be very minimal. That's why I draw a very small arrow here. Whereas for water, this difference is much greater. There's going to be a larger difference in the pull towards the oxygen than there is the hydrogen, so that's going to lead to a greater polarity in this molecule. So we can see here that water is more polar than hydrogen sulfide. And we can simply compare that by just saying there's going to be a greater pull one direction than the other in the water because of those electronegativity differences. So just like we looked at electronegativity differences to determine bond character, do we call it bond ionic, do we call it covalent, polar covalent, non-polar covalent, we can look at those same things when determining relative polarities of molecules. In fact, for this example, you might even say hydrogen sulfide isn't even polar. You could even say that because recall our cutoff for that whole non-polar bond thing is 0.4. And that happens to be the difference between hydrogen and sulfur, where these electrons are shared pretty darn equally. So we might even say there's not even any dipole here, although there would be a very, very slight one because they're not the exact same electronegativities. Alright, so in this video we've started looking at how we define polarity for molecules and how we determine relative polarities, which molecule is more polar than the other. We'll get a lot more practice with this as we look at this in class. Just keep in mind for all of these, you have to consider the geometries of the molecule. So whenever you ask yourself, is this molecule polar? If you're not first considering the geometry, the shape of the atoms and where they are, there is no possibility of being able to answer that question.